Now let's digress for just a moment and return our thoughts to the main sequence from whence we began. In the main sequence, there is an opportunity for a red dwarf star to form. Red dwarf stars are smaller than our Sun, and since they are smaller, they have less mass, making them part of the low mass group. Because of their small size, these stars burn their fuel very slowly, which allows them to live a very long time. This also causes these stars to not shine as brightly as others. Some red dwarf stars live trillions of years before they run out of fuel. And because red dwarf stars only burn a little bit of fuel at a time, they are not very hot compared to other stars. Think of a fire. The coolest part of the fire is at the top of the flame where it glows red. The hotter part in the middle glows yellow, and the hottest part near the fuel glows blue. Stars work the same way. Their temperature determines what color they are. Thus, we can determine how hot a star is just by its color. Red dwarf stars are by far the most common type of star in outer space. However, very few stars that you see in the sky are red dwarfs. This is because they are so small and make very little light. As an interesting side note for the red dwarf stage, it can be noted that a blue dwarf star is a predicted class of star that will develop from a red dwarf star after it has exhausted much of its hydrogen fuel supply. Since red dwarfs fuse their hydrogen slowly and are fully convective, the universe is currently not old enough for any blue dwarfs to have formed yet, but their future existence is predicted based on theoretical models and is reflected in the model that we've created. That concludes our discussion of low-mass stars. Now it's time to turn our focus to high-mass stars. A high-mass star is a star of about 8 sun mass or greater. Nuclear fusion of hydrogen into helium in the core of these stars occurs in high-mass stars. It's important to note the difference between high-mass stars and low-mass stars. Primarily, the luminosity of high-mass stars is much greater than that of low-mass stars. We begin with the supergiant stage. When the hydrogen at the core of a high-mass main sequence star is consumed, the star is no longer at gravitational equilibrium, and the core of the star begins to shrink, and its photosphere begins to expand. The material remaining in the core is helium, which requires a higher temperature to burn. In this stage, nuclear fusion is not occurring in the high-mass star's core, but just as in the low-mass red giant stage, nuclear burning occurs in a hydrogen shell around the helium core. In this stage, the total luminosity of the star increases. That is, the energy rate production of the hydrogen-burning shell is higher than that of the hydrogen-burning core when the star was in the main sequence. Note that in the red supergiant stage, the luminosity increases even though the surface temperature decreases. Put the Sun next to a supergiant star and you'll have a hard time finding it. Supergiant stars are the largest stars in the universe. They can be thousands of times bigger than our Sun and have a mass up to 100 times greater. Supergiants come in a variety of sizes and temperatures, but they are generally classed as being either red or blue. Red supergiants have a mass of at least 8 times that of our Sun and are generally old stars that were once similar in size to our Sun. They form from a star more than 10 times the mass of our Sun and run out of hydrogen fuel in the core, preventing fusion from collapsing it as it does, so the hydrogen outer shells begins fusion on its own. Blue supergiants are considerably hotter than red supergiants, but generally much smaller, only about 25 times the size of our Sun. Like red supergiants, they have very short lifetimes of only a few million years. They usually form when a star more than 10 times the mass of the Sun, heading towards its own demise, enters a slow burning phase. However, red supergiants can also turn blue if their own rate of nuclear fusion begins to slow down. When the core of a supergiant becomes hot enough to burn helium, the star leaves the supergiant stage. However, unlike low-mass stars that do not have further nuclear burning in the core after the helium is consumed, High mass stars have sufficient mass to generate temperatures capable of igniting the nuclear burning of carbon into oxygen. Once the carbon is consumed in the core, the star's core collapses until nuclear burning of oxygen into neon occurs. Once a high-mass star produces an inert iron core, nuclear fusion in the core ceases, and the core collapses from gravitational forces. The collapse of the stellar core to a size of just a few kilometers liberates an enormous amount of energy that drives the outer layer of the star into space through a titanic explosion called a supernova type 2. For about a week, a supernova can emit an energy rate equal to 10 billion suns, about the same as a moderate-sized galaxy. The ejected outer layers may remain visible for thousands of years and are called supernova remnant. These outer layers of the star ejected into space contain heavy elements and will eventually become part of the interstellar medium. Depending on the amount of mass in the star's core, once the outer layers of the high mass star have been ejected, the leftover core will either become a neutron star or a black hole. If the leftover core of the high mass star is stopped from collapsing by balancing gravitational forces, the star will have become a neutron star. It will have a mass comparable to the Sun, but with the size of just a few kilometers. A neutron star is a type of compact star that can result from the gravitational collapse of a massive star after a supernova. Neutron stars are the densest and smallest stars known to exist in the entire universe. They only have a radius of about 11 to 11.5 kilometers, or approximately 7 miles. And they can have a mass, though, of about twice that of our Sun. If the mass of the leftover core of a high-mass star is greater than 3 Sun mass, then neutron degeneracy pressure cannot stop the gravitational collapse, nor is there any known physical force capable of stopping the collapse. In this case, the core would collapse into what's called a black hole. A black hole is an object with a gravitational field so strong that not even light can escape it. Thus the name black hole. The gravity is so strong because matter has been squeezed into a tiny space. This can happen when a star is dying. Because no light can get out, people can't actually see black holes, thus they are invisible. In conclusion, it is important to remember that stars are like people. Stars are born. They shed their light throughout the universe. They grow old, and they die. The life cycle of stars is an important step in life itself.